What's up, guys? Welcome back to Recreational Sniper. I did not do a Firing Solution Friday this week. I was working on one, and in the middle of working on it, I realized that my math has been wrong for a couple of things. And then I actually did an experiment with changing the way that I did some of the math, and I was able to find a new way to do it that actually reflected what our real world observations have been. So I will do another Firing Solution Friday next week when I rework the math out, but I just kind of wanted to explain that, and I will do another video explaining exactly what happened and what was wrong with the math and then how I fixed it. But today I thought I would show you guys something new that I've been working on. And basically this right here, which I actually have a bigger version of it here. Sorry, we're outside and the thunderstorm's rolling in. But this is, I combined a compass rosette, which has all the degrees on it. And I know this seems backwards that it goes 0, 10, 20, 30, 40 to the northwest instead of to the north, east. And so it's like a counterclockwise type of deal. But when you're shooting an azimuth or whatever, for your correction fire for vertical coriolis, 330 degrees gives you the exact same result as 30 degrees, so it's really not that big of a deal that it's backwards. And I also combine this with a clock face, so you'll notice 12, 1, 2, 3, 4, 5, 6, etc. And that is for wind angle of fire correction. And I actually, if you look real close, your 1 o'clock and your 2 o'clock and your 3 o'clock out here, that is, those little numbers out there are actually your angle cosine values. So if your full value is obviously at 3 o'clock or at 9 o'clock, and then your zero value would be north and south for that, and then it gives you your values for in between. So like at 1 o'clock it would be a half value, at 2 o'clock it would be 0.866% or 86.6% of a full value. And then I just also have the same thing on a smaller on a little bit smaller, and I actually have the formulas for spin drift, horizontal coriolis, and vertical coriolis on here, just to keep up with my paperwork. So let's do a hypothetical shot. Sitting here at the house on my front porch, I'll show you how this is going to work. Alright, so you need a couple things. We need a GPS or a compass. The GPS does give you a little more information, but a compass will work. And you need a anemometer, and you're going to need that for your barometric pressure. Now, as I've said before in different videos, your barometric pressure is independent of altitude. Your barometric pressure can change while your altitude stays constant. For instance, like right now, we have a storm system coming through, and storm systems usually both have either in the front or the rear, they will have a high pressure zone and a low pressure zone, and which can swing your observed, actual measured barometric pressure. It can swing your barometric pressure by quite a bit, depending on if the storm is coming to you or if it's leaving the area. So that's pretty neat and pretty cool, but it's also the reason why we want to change things a little bit. So my system that I've got going on is ever evolving. I'm constantly trying to make improvements and make it more accurate and better and somewhat more simplistic. And so I've now reworked my charts to where they only work with barometric pressure, and that we don't try to use altitude to determine barometric pressure. we really actually don't really have to worry about the altitude at all. It's not really that important, but the barometric pressure is, because the barometric pressure does change. So right now, according to this, we'll give you some of the stats out here. We're at 85.1 degrees Fahrenheit, and the humidity keeps changing quite a bit. I've had this thing on out here for about 10 minutes, and it's ranged between like 80% and 67% or something, and now it's going back up. But we're about 85 degrees, and we keep getting a mild wind, a mild breeze. It changes directions from like up to 2.5 miles an hour or so. Alright, so as you can see here, the barometric pressure, it's showing 2947. Literally 5 minutes ago it was saying 2941, and the altitude is also changing a little bit with that. So let's see, yeah. So basically we just want to make sure we know what the barometric pressure is, and we're going to write that down. So temperature is 85 degrees Fahrenheit, and barometric pressure is 29.47 currently, and I think it's trying to bump up to 48, but 29.47. Alright, so say we want to take a shot, and we want to take our shot straight down my driveway all the way that direction, okay? So let's determine, first we have to determine north and then our direction of fire, okay? So I'm going to use the GPS here. And we can actually check our altitude. See, according to the GPS, it's saying, which it's a little bit bright, but it's saying like 510 feet according to the GPS where I'm located at. And according to the barometric pressure, we're actually at like 411 feet. So there you go. Your barometric pressure cannot really be calculated off your altitude. Okay. So what we want to do is we want to get out our compass, and we want to determine which way is north. And so north this thing's a little bit slow to pick up sometimes, but ideally we would use a compass for this, but this will work. So north is about that direction. So what we want to do is we want to take this rosette and we want to point it towards north. So that's north, and then we're going to figure out which direction we're firing. And so we're actually firing, if you lay this down in the middle, we're actually firing about right there, which according to this would be about 278 degrees. We'll just call it 278 degrees is our azimuth. And we will need, not Fahrenheit. 278 degrees is our azimuth. So that is the direction we are actually firing. Okay. Now, as far as using this to determine our wind angle, we can line up north and south as if, you know, that's the position the rifle is shooting, because our clock face works this way. And now we're not worried about north, south, east, and west and all that. We're worried about the angle of the clock face here. And we can determine that the wind is actually coming just about straight at us, so we have about a zero wind deflection as far as horizontally. All right, so let's go ahead and get into this. So we're at 29 point. Yeah, see, now it's saying 29.48. 29.48 inches of mercury. So we're going to look at our 30-inch of mercury chart, where you can see it there, it says 30. And then we're going to look at our 29-inch of mercury chart. And the reason why is because we are at an altitude that, or a barometric pressure that's in between those two zones. So hypothetically, let's just say that we are going to shoot 1,300 yards even. Alright, so our 30-inch mercury zone will tell us that we need to come up 19.9 mils, and that's at 30 inches of Hg. And then for 29 inches of Hg, we need to come up 18.7. So that's over a whole mil of a difference there from 30 inches to 29 inches. So now we need to determine our real correction for where we're at, and we are 0.48 inches of mercury in between those two zones. So what we're going to do, and this is actually where we're going to work on fixing some of the math and doing it the right way instead of the way I was doing it, which basically I've been telling you guys the wrong way to do things, and it's not going to be the most accurate. So like I said, ever evolving and ever improving system here. So we're going to take 19.9, we're going to subtract 18.7, and then we're going to get, what is that, 1.2? And then we need to take 1.2 and we need to multiply it by 0.48. So 1.2. Sorry guys, I know it's getting kind of dark out here, and the camera's not going to pick up most everything. So multiply 1.2 times 0.48, and we're going to get 0.576. Alright, now I was, in previous settings, I was actually saying to take this number and add it to the low number here. Okay, but that is actually incorrect. It will be much closer to reality if we take the high number and we actually subtract this. And the reason why, and I determined the reason why this is the way to do it, is because of the parabolic arc of the bullet flight, its flight path, its trajectory, is that your ascending leg is longer and not as steep as your descending leg. So the further you get out there towards the target, the more the bullet's dropping over a shorter distance. Okay, so, and I actually, when I reworked the math on Garen's drop charts, and I kind of reworked his drop charts too, but when I did the math, the one way of adding it to the low number, it actually told me that the elevation value was actually less than it should be. What we observed like 36 minutes of angle is what he needed to come up, and or is what he ended up coming up to, and what the math was telling me was that he needed to come up like 34 or 33 minutes of angle. But when I reworked it and I actually used the high number and subtracted the value that math problem was giving me, it actually gave me 36.1 minutes of angle is what he needed to come up at. So it was like almost dead on accuracy wise as far as that math goes. So I will explain that whole deal in another video, like I said. So I'm going to get back to this. So now we're going to take 19.9 and we're going to subtract 0.576. And that's going to give us 19.324 mils is our actual correction. So we need to come up 19.324, so we can round that to 19.3 mils, and that would be our actual vertical correction for the direction we are shooting. Now, what about Coriolis effect? Because now we are shooting 1,300 yards, right? For our this, you know, and the direction we're shooting is 278 degrees. That's our azimuth. So let's go ahead and run our vertical Coriolis math problem here. So find the sheet that actually has it on here. So our vertical Coriolis formula is our omega constant multiplied by the range in feet, multiply that by the time of flight, multiply that by the cosine of the latitude, and then multiply that by the sine of the azimuth, and that will equal our vertical Coriolis. Now there's one thing we need to do between these two charts is we need to figure out our time of flight average for 29.48 inches of mercury. Okay, so our time of flight at 1,300 yards for 30 inches of mercury is 2.595. At 30, and at 29 inches of mercury it's 2.511. Now, you could take a rough guess and get pretty close, just in between there. But if you really just want to do the math perfectly and get it right, basically we'd do the same thing. We would take 2.595, we'd subtract 2.511, and that would give us 0.084, and then we take 0.084, multiply that by 0.48. I don't know, this is getting a little bit crazy here, but 0.084 multiplied by 0.48 for the difference, and we get 0.040. It's 0.04032, but I'm not going to run out that many place values, okay? It's just a little bit ridiculous for seconds anyways. Like, we're talking 400ths of a second difference. So now we're going to take 25.95 and subtract the 0.040, and that's going to get us 2.595, and that's going to get us 2.555 seconds is our time of flight. Okay, so we know our time of flight, we know our azimuth. We don't know our latitude right now. We do need to find out what our latitude is. So in our GPS, we can go here and it will tell us, hang on, let's see, go to the map. Alright, we can just put a pin there And up in the top corner, I know you can't see it, but our latitude is 34.61523 degrees north. Okay, so we got our latitude, our time of flight, and our range in feet is pretty easy to figure out. We're shooting exactly 1,300 yards, so we just take 1,300 and multiply that by 3 feet, and that's 3,900 feet. Okay, so now let's work out our problem. Our omega constant is always 0.0000729, and we're going to multiply that by 3,900 feet, and multiply that by our time of flight, 2.555 seconds, and then we're going to multiply that by the cosine of our latitude, cosine of our latitude, which is 34.61523, and then we're going to multiply that by the sine of our azimuth. So sine, and then our azimuth was 278 degrees. And this should give us our vertical deflection in feet. And then we will have to convert that to mils so that we can index it on our scope. So 0.0000729 times 3,900 times 2.555 times the cosine of 34.615239 times the sine of 278 degrees, and we get a negative number, negative 0.592. So that's 0.592 feet. So (12 inches in a foot divided by 0.592. Oops, shoot. 12 divided by 0.592 is... I did that wrong. Okay. 12 times 0.592, so half of that, basically, is going to give us 7.104 inches of vertical coriolis, shooting the direction that we're shooting, because we're almost shooting east, so we're going to have a lot of vertical. And because we are shooting east, the target is actually going away from us, so we're going to hit high, which is the reason why this is a negative number. That means we actually need to come down 7.104 inches. So now we need to convert that to mils. 1 mil at 100 yards is 3.6 inches, and we're shooting 1,300 yards, so 1 mil at 1,300 yards would be 3.6 times 13, and that is 46.6 inches. Or sorry, 46.8 inches. So 1 mil at 1,300 yards is 46.8 inches. Okay, now we do 7.104 divided by 46.8. And so basically, we need to come down 1.65. Oh shoot, I hit too many numbers in there. 7.104 divided by 46.8. I knew that sounded crazy. That was way too much. We need to come down 0.15 mils. Actually, it's a hair over that, so you could round that to 0.2 mils, or you could just go 0.1 mil, which would be basically one click in the scope. So we would take, it says we need to come up 19.3, we would actually come up 19.2 or 19.1 to 19.2, somewhere in there, just depending on how you wanted to round it. So that would be our solution for shooting, and that's our vertical correction, our total vertical correction for 1300 yards, given the azimuth that we're shooting and our barometric pressure that we have and everything like that. I didn't get into the temperature thing because it's 85 degrees, so it's pretty close to the 80 degrees that we worked up for this. And so that's how you do that. That is our correction for that. Now, as far as spin drift and that sort of thing goes, we can look at that if you want to. It's pretty easy to determine. You're going to do the same thing here. We're going to take our gyroscopic stability, and at 30 inches, our gyroscopic stability is 1.66 for our particular bullet, and at 29, it is 1.72. So the lower the barometric pressure, the higher your gyroscopic stability factor is. So you take 1.72, subtract 1.66, what was that, 0.08? No, it's 0.06. 0.06. 0.06 times 0.48 is 0.028, but we're gonna round it up. It's 0.0288, but we're gonna round it up to 0.029, and then we're gonna subtract that from, which we would basically just round that up to 0.03. And then we take 1.72 minus 0.03. We get 1.69 is our corrected gyroscopic stability factor. Now, our formula is going to be 1.25 times 1.69 plus 1.2 times our corrected time of flight of 2.555, and multiply, or actually raise that to the power of 1.83, and that will give us our spin drift in inches. And since we're a right hand twist barrel, our spin drift is always to the right. So 1.25 times 1.69 plus 1.2 times 2.555 raised to the power of 1.83 equals 20.106 inches is our spin drift to the right at 1300 yards at 29.48 inches of mercury. So now we need to convert that to mils, and like we've said before, 1 mil at that distance is 46.8. So as you can see, doing all this previous math kind of helps the more you get into this. So we're going to take 20.106 and divide that by 46.8, which is, at that range, is 0.43 mils of drift to the right. So what we would do is we'd click back left 0.4 mils. You may or may not want to go an additional tenth of a mil to 0.5. It's up to you. I typically just, when it's that close, I'd round it down to 0.4. So that's our drift, our spin drift at that range. Now, since our wind angle today is just coming straight at us, there will be a very slight vertical effect as far as the wind goes, but there will be no left or right effect on the wind. And since it's coming straight at us, that's going to mean it's going to kind of push our bullet down a little bit. So it's going to hit just a little low, but we're talking very, very small amount at 1,300 yards. You know, maybe a ½ inch for a 2-mile-an-hour wind, something like that. It's going to be very, very small. But yeah, there you go. So for this shot, we would come up 19.2, or somewhere between 19.1 and 19.2 mils, and we would correct left 0.4 mils for our spin drift. So there you go. This kind of shows you that making the charts and only worrying about the barometric pressure is way easier than having to try to convert altitude to barometric pressure. That's a very hard thing to do, and it's not constant, so there can be a wide range of error doing it that way. This math is still not perfect, but it would definitely get you on target. So there's really no just super perfect way of doing things. And then if you start throwing in variables like extreme angles of fire, like uphill or downhill, like shooting through multiple barometric pressure zones, then you know your things change quite a bit when you do that, as far as your ballistic coefficient and your drag and your stability factor and that sort of thing. It's really hard without a super good computer to map all of that out, where those changes occur in the flight path of the bullet. So the best we can do really is this kind of math. And for the reasons of not using ballistic software, I actually like doing it this way. Of course, I don't have a ballistic solver. I've used them like in my phone. I've used phone apps before, but I've actually found that a lot of times doing it this way is better. It takes longer, obviously, but those problems with those ballistic calculators and solvers is that if you don't get every input in just right, they tend to basically, if you put garbage in, you get garbage out of it. Here's the rain. And they don't really, a lot of them don't really calculate for coriolis, vertical or horizontal coriolis, and a lot of them don't really calculate for spin drift either. They just don't have the input options for your bullet and your barrel twist and all of that. So doing it this way is actually a better way of doing things to get a much more accurate firing solution. Those ballistic calculators are fast, but more than likely you're not going to get a first round hit on the target using one. You are going to probably have to make a correction. So our goal here at Recreational Sniper is to make first round impacts on any target at any range. We don't want to have to make second round impact, second round corrections and that sort of thing. So my goal is to try to get the math as good as possible to be able to calculate very, very precise firing solutions. So with that being said, I want to thank you guys for watching, and we'll see you next time in the next video.